All right, so welcome everyone. This is the first time I think that we tend to advertise this as being 5 p.m. Pacific. This is the first time I've actually hosted this on Pacific time. I'm in San Jose for, you see this, the NVIDIA GTC conference. Been here since Sunday. It's been pretty interesting. I've been to the past maybe 3 GTCs. Of course, the conversation here is all about new GPUs and how we accelerate training, and we can talk a little bit more about that. But here's our agenda for the meetup. This is kind of our standard. I'll go through some brief introductory remarks that'll get us to about 5 minutes, and then we'll kind of open mic it for another 10 minutes. And then I will hand the baton over to Rongmin for our main presentation. A quick update on upcoming meetups. If you don't know, we do 2 meetups. One that is timed around evenings in Europe, Middle East, and Africa. And our presentation will be by Samujwal Ghosh on matching networks for one-shot learning. And that's, need to get the exact date for that. It's early April. That's when we do the EMEA meetups, and the Americas meetup is mid-April. And that'll be William Horton on averaging weights leads to wider optima and better generalization. Of course, you're invited to respond to our meetup call for papers. That's the link there. Rongmin, so we've got in the kind of rough agenda, we kind of say question and answer for 15 minutes at the end. I need to change that. It never works out like that. I'll usually ask questions in between and kind of open it up for questions. I'll also monitor the chat for people that submit questions via the chat. You don't have to worry about that. You just worry about presenting, and I'll make sure you see any questions.
Okay.
So to kind of kick off discussion time, these are some of the topics that tend to come up. Questions and comments on recent podcast episodes. Of course, feedback on the podcast, topics and guests that you'd like to hear about or hear from, updates from you and the community on things that you're working on or things that have caught your interest, interesting new ideas or papers or projects, news items that you've seen, anything that's generally caught your interest from last time, or questions that you have that other people in the community might be able to help with. So any takers to get us kicked off?
Sam, did you have a look at the Jetson, the AI, the NVIDIA, the Nano, the new $99 device that they've released for the masses?
Yeah, so they, I don't know if I would call this for the masses. So they released this $99 kind of edge machine. It's basically, think of it as like a Raspberry Pi with a GPU, right? And so, where I would position Raspberry Pi is like for the masses, but low performance. This thing is $99 if you're trying to ship at scale is kind of a lot. But it is a really interesting device, and I got to put hands on it just an hour and change ago. They're actually selling them here. You can buy them. I'm very tempted to pick one up, but I do have, there's like my stack of books, and then there's my stack of devices to play with that I never have a chance to play with. And so I'm not sure that I want to add another thing to that stack, but it is a really, I don't have any of the specs in front of me, but it's an interesting proposition, and pushing the costs down fairly low for what I believe the performance is, pretty decent. What did you think when you saw the announcement?
No, I think it's pretty exciting because what will really happen is, I think a lot of schools and educational institutions will start introducing educational courses. My only point is NVIDIA has not really been at the edge of development frameworks. Somebody, maybe somebody like a Jeremy, or maybe Google could, or Microsoft ideally could pick it up and build a low cost development kits on this. So I see the whole area expanding in a very huge in a very significant manner for the school, for the educational segment.
Mm-hmm. So
And
NVIDIA is investing a lot in the developer ecosystem. Obviously, it's been a big part of what they're doing since CUDA.
yeah,
But I think their strategy with Jetson and with the platform in general is not to make it so that they have to build specific tools, but to engage with communities like PyTorch and TensorFlow
right,
so that it just kind of works, right? Those frameworks have the CUDA support all built in, so you can kind of deploy, you can use TensorFlow as your developer framework as opposed to, something specific that NVIDIA is trying to give you. They did do
yeah,
some kind of deal with Amazon so that I think you can deploy this. I'm just like, I didn't see the detail here. I just kind of overheard it. But the gist that I got was that you can like build models in SageMaker and kind of deploy them out to, I believe it was this device via like Greengrass or one of the other IoT solutions.
yeah.
If I'm wrong, somebody correct me, but I think I heard something like that.
Yeah. No, in fact, I had attended one of the sessions in India about 6 months back, and I had asked them about their cloud strategy. So they weren't very forthcoming about it in terms of. So a device like this, along with let's say inference happening or backend services happening on the NVIDIA cloud, because they have the credibility and they have the size to really drive the whole business to a different a
Mm-hmm.
new level altogether.
So
So it'll be interesting.
NVIDIA's cloud strategy has been really confusing because 2 years ago, I believe, they came out with this thing called NGC, NVIDIA GPU Cloud.
Yeah.
But it's not a cloud. It's not hosting workloads. It is where it's evolving to is like if you know Docker Hub, a container repository,
Right.
it's more like NVIDIA Hub. They're
Okay.
pushing containers for their Kubernetes distribution. They've got this thing Clara, which is a kind of a process, kind of healthcare data science process toolkit, if you will. You can do data cleansing for imagery and all kinds of stuff. That's Clara. They've got Isaac, which is, or Drive. Isaac, I think, is simulation, and Drive. They've got Drive is on the autonomous vehicle side. So they got all these software tools that sit like above the infrastructure layer that provide specific kind of, it's like more solution oriented for healthcare and autonomous vehicles. And they're not selling any of this stuff. They're just using it to drive value on the platform. And they
Okay.
push it all to this NGC.
Okay. Okay.
And you can, I don't know if they're still supporting this, but you used to be able to use NGC to like spin up these things in your AWS and Google, your own AWS and Google accounts.
Okay. Okay.
I think now AWS and Google have all of the like low level images, so I'm not sure if they're still doing that.
Okay.
But it's, yeah, their cloud strategy, has been a little murky and confusing because
Okay.
of in a large, in not small degree, confusing nomenclature.
Okay. Okay.
So what
What are
else
the
is on
other?
everyone's mind? Everyone's shy today. Mahesh and Rongmin, you are the only two on video, and everyone else is shy.
Yeah.
Srivastava was speaking earlier. What's on your mind?
So currently I'm reading few papers on attention and NLP, and getting like extremely fascinated with that areas. I haven't implemented the papers. I have not come to the point where I can read a paper and start implementing it. So I'm kind of struggling first to get used to of reading the paper, and then I'm not sure when will I come to a point where I just read the paper and start implementing.
Well, isn't that the promise of part 2 of Fast AI? Is that at the end of
Not in this one is this part 2 is about engineering.
Oh, okay.
It's not about paper implementation.
Oh, really? Interesting.
Yes, that is the interesting.
I didn't catch that change.
Yeah. This time it's not. It's like a fundamental. He's just doing the fundamentals about gradient descent and all those like foundation using programming.
Oh, wow.
Yeah. I mean, like, it's not like he comes there and implement a magical paper and then you be all mesmerized with that. It's not like that. Yeah.
So you've been studying attention. Is it true what they say that it's all we need?
No, actually, there are much more. Yeah, actually. Apparently, there is another paper. They say like attention is not exactly all you need. So I mean, like, it's so the field is going so fast.
Yeah.
I mean, you don't know like what exactly. Suppose you are reading an attention paper today, and you are not sure if you are reading a deprecated version of some technology.
Oh, it's already deprecated when it's published.
Yeah, exactly.
Yeah, I was talking to some folks here. So I was talking to the product manager for NVIDIA's like infrastructure and Kubernetes stuff. You all know that I've been spending a lot of time on that. And we did the eBook on Kubernetes. And,
oh, really? Kubernetes and what? What did you do?
Kubernetes for deep learning and machine learning. So
oh, really?
ML platforms and infrastructure. Yes.
Oh, I will search it. Is it available online?
It's on the TWiML.com website. And I've done quite a few podcasts on the topic, but we published this ebook in November, right before the last KubeCon. And it's only been a couple months, 2-3 months, and it's already way out of date. Like Kubeflow's renamed a bunch of stuff. One of the companies I mentioned no longer exists. There's all kinds of new tools and stuff like that. The space is moving so fast. But I don't want to eat too deeply into Rongmin's time. So I'm going to turn actually, I messed up and did not change the title here. So I'll go back to our title slide. Rongmin's going to be presenting on automatic differentiation and differential programming. And these are the papers that he's going to be presenting. If you want to have not already grabbed these, TWiML.com/meetup is going to be the best place to just click through to these archive links. So with that in mind, I'm going to stop sharing. And Rongmin, thank you for your presentation, and take it away.
Right, thanks, Sam. Thanks for having me. So this is just going to be a short introduction about how automatic differentiation actually comes up in machine learning, I think. And I'm just gonna, am I sharing this?
I'm not seeing it now.
Not seeing it. Okay, right. So I need to go to Zoom and share that. Okay, right. There we go. Right. So So if you don't have the papers on hand, that's fine. I'm probably going to share that on my screen as well. And I'll probably introduce some more papers along the way. Probably Sam can put that up if it's I might send an email or something.
Yeah, we'll put the slides up and anything else you send in the Slack.
Right, the Slack. Okay, right. So so I'm going to be talking a little bit about differentiable programming and really automatic differentiation for machine learning. So first question is, what's differentiable programming? Anybody has any responses? Because I've heard quite a bit. Although this is probably the one that I've heard about a lot. Yes. Once upon a time, well, apparently from January the 5th last year, apparently Yann LeCun posted this, basically saying deep learning is dead, long live differentiable programming. Of course, I think most people are saying, well, this is going to be a buzzword, isn't it? And he's reflected as a buzzword, and I think most people didn't think much of it. But that's not all he wrote in that Facebook status. This is the full status. Yeah, I was like, okay, maybe I should read this. So this is what he actually wrote there. Can you see that on the share? Because I think I switched over to the share. Yep. So it claims that differentiable programming is little more than rebranding. But the important point is that when we're doing machine learning, what Yann LeCun observed is that people are now building a new kind of software. They're actually assembling networks of parameterized functional blocks. Basically, the thing is that you can think of each neural network as, like just basically like chunks and chunks and chunks of functions that are parameterized by the data that you're feeding it in. But they're also parameterized by like if the layer in the middle, so like the invisible layer, then what you're feeding in is other functional blocks. So you're feeding in not just data, which is like the layer that that accepts the data that's coming in, but for the intermediate layers, the layers that are not visible, you're also feeding in parameterized functions that come from the previous layers as well. So already you're kind of forced to think in a more functional programming way. And then, the second bit is, of course, like training them for examples. That's the data bit, using some form of gradient-based optimization. That's where the automatic differentiation comes in, right? So, people are defining the networks procedurally in a data-dependent way, and you have control flows as well as loops and conditionals, and you want these networks to change dynamically when you change the input data. So it makes things a lot more complicated, which is why we're seeing, which is why initially we have all this like, oh no, like AI is this black box, we don't understand what's going on, there's millions of parameters, things like that. So it's because like it's highly parameterized, and you want to optimize it. So, and the thing is that because you're using gradients, it's automatically differentiated. So And the thing is that like dynamic networks are also becoming increasingly popular, particularly for natural language processing. That's the NLP over there, because with FAL, I mean like if you look at Google Translate, they're on version 2.0 right now. A few years ago, they've upgraded the network. So that's great for East Asian languages in particular, because you have all these like weird grammatical structures that don't really get translated that well when you're using something that you've trained on Western European languages, and then on Eastern Asian languages, there are things that don't work that well. So these new machine learning models are helping it to work better. And so what really Jan-Le-Cun was saying in differentiable programming is that you're dealing with parameterized functional blocks. There's gradient-based optimization, and then people are, well, 1 year ago, they're working on compilers for imperative differentiable programming languages. And we're going to see a manifesto for a general purpose programming language later on in the talk. And you're welcome to guess as to which language it is. It's a language that I've heard of before. So keep guessing. But yeah, so that's what Jan-Le-Cun was referring to, which is that people are actually working on compilers for imperative differentiable programming languages. Right. And right. So trying to there we go. Are you seeing this?
Yeah.
Okay. Right. So although of course like the history goes back just a little bit longer, which is that in 2015 Christopher Orloff wrote on his blog. You know, it was a very speculative piece, but already like in 2005, Cola, as he like still call himself online, has already seen that like there are all these like functional programming idioms that are appearing when you're looking at neural networks. So yeah, so you have all these, yeah. So basically the thing is that it's just like, sorry?
The next slide isn't coming up. We're seeing like your browser's address bar or something.
Is it?
Or status bar.
That's weird. I can see it. I can, oh, hang on. Can you see this now?
Yes.
Okay, right. So this is Colin's blog from 2015, and so basically and he basically makes some observations, like for example, encoding recurring neural networks are what's known as folds in the functional programming community, and then you have like generating recurrent neural networks such as unfolds, and like there's a whole list. It's basically listed a whole bunch of neural network patterns, and you just see that like you've got all these functional programming patterns that come up, and so what he's what is speculated at that time, back in 2015, it can be, you know, like all the models that we're training can be seen as a kind of differentiable functional programming. So it's really what people have been doing in neural networks seems to be a natural intersection of functional programming and optimization. So, and the thing is that it's just like, since then, I think like there's been a gradual shift, a paradigm shift, if you will, to making programming languages more functional. So we're using application now that's running on a language that has been gradually shifting towards the functional programming paradigm. That's JavaScript. It's an ES6 right now. ES6, ECMAScript 6, 7, or 8. Can't remember. There's been a lot of updates to JavaScript right now, such that it's almost unrecognizable to people who've been working with JavaScript 20 years ago when it came out, if they haven't been keeping up with developments there. So there's been this, so this is more or less what I understand of the history of differentiable programming. So now, going back now to are you seeing the differentiable functional programming slide again? Yes?
Yeah.
Yeah, okay. So then the question becomes, what is automatic differentiation? So a lot of differentiation that's done before, and I mean like a lot of things that are interesting and have numerical applications, these come under what's called numerical differentiation. So you're looking at calculating derivatives using approximation function techniques. It's useful usually because it's really hard to because probably, like, for example, you have some really exotic function and you don't actually know how to calculate the derivative because you don't know. You just don't know. And so you use approximation techniques like finite element method or something like that. And then you try to calculate the derivative of the function because you want at a particular point because you need the value of the derivative at a particular point for your applications. For symbolic differentiation, that's trying to get the computer to calculate derivatives by manipulating the mathematical expressions and formulas themselves. So that's more or less pretty much what we did in high school or in first course in calculus. So basically, it's just like if you have x to the power of n, you differentiate it, you bring the n down, and x and minus, and then lower the power by 1 and minus 1. And so we've got all these rules that allow you to manipulate. And for automatic differentiation, what you want is to do something that's similar to numerical differentiation, in that you actually want to get a value of the derivative at a particular point, but you want that particular value to have as little error as possible, especially because for example, like say you want to calculate lots and lots of gradients for a machine learning application. So the thing is that you will end up incurring a lot of errors in terms of like roundouts, or because of various constraints in your computing architecture, then you lose accuracy in that way. And so what people have been doing since the 1960s is to try to come up with ways by which we defer the calculation of the value of the derivative as far as possible until we actually meet that value, and then we calculate it. So, and the thing is that it's just like, and you could, for example, you say like, look, programs are just functions, right? Like you put things in and then you get things out. So like, I mean, a lot of programs are built using functions. So what if we can calculate derivatives for those functions as well? You might want to do that because, let's say, for example, I have a program and it's just basically a complicated list of mathematical functions. Then, like, you want to be able to take the derivative of that, for example. Or let's say, or in particular, like with all those neural network patterns that I've seen before, these are actually patterns in functional programs. So can we take the derivatives of those things as well? Maybe you can. So that's the point of automatic differentiation. It calculates derivatives by manipulating program blocks. And that's what you see in packages that we have like TensorFlow and PyTorch and various others that are out there. So, so you want to be able to do automatic differentiation in that way. So there are two ways you can do automatic differentiation. So the easy to implement way is for no automatic differentiation. The only problem is that the chain rule will guarantee that if you're not careful, you can get a combinatorial explosion. The solution, as it turns out, is to write something, write that expression in what's known as an A-normal form. And so I'm going to so I'm just going to switch over to this paper that is the first paper on that list, and I'm going to do a new share. Where are we? Right, this one. Can you see this paper? The Demystifying Differentiable Programming. Okay, right.
Yes, we can see it.
Yep, thank you. Right, so this. Right. So over here, that's the actually page. No, actually. Scroll. So this is the combinatorial explosion that I've shown in my slides, and that has a well-known solution, which is that you rewrite all the expressions over here in this form. Let y1 equals to something in blah blah blah. Let yn equals to something in blah blah blah, and then let z1 equals to y1 times y2 in let blah blah blah. And so this particular form over here is known as administrative normal form, and this is a intermediate form, intermediate representation that is frequently used in functional programming, in compilers for functional programming languages. So this demystifying differentiable programming paper is written by a team headed by Tiak Rumpf, who's one of the developers for Scala. And the language that they're working with is Scala. So I think Scala is used in big data applications because of because people want to use Hadoop or other
Spark.
Spark. Yeah, like these frameworks that actually use Scala. So so this is the contribution that Wang make here, that they've built this thing. So that's kind of the grammar that they've come up with, and that's how they implemented forward mode automatic differentiation in Scala. So so they overload plus and multiplication. So, and then they define new number type, which is basically the original value itself, that's x, and then an adjoint value. I think they call it adjoint. And then they have they overload the plus and the multiply operator with this formula. There are other things, of course, like you have to define, you have to register all the for every elementary function that you have. Say, for example, sine, cosine, which they've not treated here. You've got to say, well, okay, so what are we going to do with sine, cosine, and exponential functions, stuff like that.
Quick question.
Yeah, go on.
I'm not able to understand why. So because they think that this differentiable programming or whatever automatic differentiation is the future, that's the reason they are adding all these APIs into Scala documentation, or that's the way. What is the goal of adding these APIs into the documentation? Do they want the Scala people to use the differentiation? Do they see it as a futuristic approach, or do they want to club the deep learning with the Scala? What exactly is the goal here?
I think there's definitely a demand. I think there's a demand for people who want to do this. I'm not sure how big the demand is, but there is probably some demand, which is why Tiakurov is doing it with his team over here in this paper. It's actually a really good question, and it actually leads on to the next part of my presentation. The holy grail is, if you will, to actually achieve greater speedups, because right. So let's see.
What was that you said? To achieve what?
Greater speedups. Greater speedups. Actually, I've treated this in my slides. So let me go back to my slides. Yeah, and I'll have to share again. Yep. Are you seeing the forward mode AD slide again, Sam? Yep. Okay. So what we usually want is for machine learning is reverse mode automatic differentiation, reverse mode AD, which is a little bit more complicated to implement. I'm frantically sweeping a lot of things under the carpet because it's going to get a lot more complicated. So this is going to be a rather pared down. So if you're looking,
the only one that missed a bunch of that. Your video and audio froze for a second.
Oh.
But I think you were just saying that it gets really complicated.
Yeah, it's just getting very It's just getting very complicated, and actually the thing is that it's still an active area of research. Because there's still some problems that haven't been solved yet, but people are still chugging along. I haven't seen any catastrophic breakdowns, so maybe the problems are not that big. So anyway, reverse mode AD requires both a forward forward pass followed by backward pass, and this backward pass is usually what's referred to as backpropagation, in the sense that it's just like after you've done the forward pass, you propagate all the values backwards down the chain that you've come up with. So for this, you need to generate and store intermediate values. And classically speaking, this is stored in auxiliary data structure. So the programmer would usually have to define a separate data structure that's usually known as a ranked list or tape. So to answer the question that I just got earlier, the whole point of all these things, trying to come up with compilers for differentiable programming languages, is that tapes can be expensive, especially if you're the one who's writing it, because then you're running this on top of the compiler. And the thing is that it's just like what you're keeping track of is that you're keeping track of every function that has ever been called when you're actually computing an expression. So like you're keeping track of every addition, every multiplication, subtraction, division, exponential function, trigonometric functions, whatever it is, you're keeping track of this in that tape. This is an auxiliary data structure that you've actually handwritten into your code. But the thing is that this data is actually being tracked elsewhere. It is being tracked elsewhere. Where is it being tracked? It's in the compiler. The compiler is tracking all these things for you because he has to. He has to, because you're making function calls, you're making tail calls, if you're doing imperative programming, you're making the equivalent of go-to statements, for example, and the compiler has to keep track of all these things. And more or less, the compiler is working symbolically. So who better to do all this work for you, in a sense, for free, than a compiler? And so that's why this whole differentiable programming thing, that's the whole idea, which is that it's just like, like the compiler is already doing all these things, it's tracking down every single function that you're making it do. It's tracking all the arithmetic operations and all that thing. So that's why you're seeing all these like new all these new things, because the compiler is doing all the is handling all the intermediate representations, whether or not it's like in ANF form, or whether or not it's in the form of computational graphs and whatever. So the thing is, yeah, to quite a lot of people who've been thinking about this, as from Christopher Ola onwards, it seems like a natural thing to do. And in fact, it has already been done in 2008 in a paper by Perlmutter and Siskin. And I've got to do a new share. Which one is it? Yep, this is the one. And they've done a functional framework. So they call it Lambda, the ultimate backpropagator. And you can see like all these depictions of transition functions and all that kind of thing. But they've already done it, and this was in 2008. Unfortunately, of course, they did it in a language. Sam, you're still seeing that paper, right?
Yeah.
Yep. Okay, good. Yep. So unfortunately, they did it in a dialect of Scheme, which is the dialect of Lisp. So not sure if I've said anything wrong at this point. Forgive me.
So basically, what you are trying to say is that instead of making compiler do this ranked list or whatever, that tape processing, we are moving that whole processing to a higher level programming language in Scala.
No.
So you are giving these capability to the programming language instead of the compiler doing it, processing for us? What exactly, how are the...
Yeah, Yeah, the idea behind all these things is to try to get the compiler to do it, right? The compiler to keep track of that tape, that dollar structure.
Keep track of automatic differentiation by compiler.
By the compiler, yes. So we
And
actually
we have high-level API to make that happen.
Actually, the goal is to actually like get the compiler of your programming language to do it for you.
And where is the definition of compiler? Like suppose I'm writing a Java compiler or whatever, then where exactly is the where is the protocol of how they are going to write this thing, or it's already in every programming language?
Well, I mean, like, so for example, if we're looking at there already for this paper that I've been pointing you to, they already have such a compiler. It's a custom compiler, and basically the thing is that it's just like it does that for you automatically. Unfortunately, it's not in Java. It's in a dialect of Scheme, which nobody uses these days. So,
I'm assuming it's related, but with TensorFlow, I don't know if this is just a function of TensorFlow, the 2.0 alpha, or if this has been around for a while, but there's this function notation or function decorator that you can do, or function mode. I'm not sure the right nomenclature, but that if I remember correctly, it's like allowing you to manipulate the tape. And when I first heard them talking about that, I wasn't really sure what tape they were talking about. Now I'm making the connection to what you're describing here.
Yeah, the tape is basically keeping track of all the functions that have gone into actually building your whatever is it, whatever expression it is that you're trying to calculate. So I mean, like in TensorFlow, they keep track of the tape by just by keeping track of the computational graph. So
right.
The computation.
But in this example, TensorFlow would be an example of the compiler that is keeping track of the tape.
TensorFlow is a compiler.
I'm not quite sure what the architecture of TensorFlow is. So, but I think it's more like it's a library that you plug into your favorite programming software. Language, I think they have bindings for different languages as well. So it's a library that's actually, TensorFlow is actually a library that's written in C++, I think.
Yeah, I guess there's this LLVM compiler thing, which maybe only applies to the Swift stuff.
The idea here is that like people want like an implementation of automatic differentiation that's kind of like as native to their programming language as possible. So the idea is that like instead of having a Wanged list or a tape at a high level where the programmer is actually like doing it, and so that tape is being tracked at a high level, you want to get closer to the metal. You want to go lower. You want to get the compiler to do it for you. And so then it's just like, because there are lots of people, quite a lot of people out there who are doing compiler optimizations. So then if you more or less outsource the tracking of that tape to the compiler, then like, the people who are writing compilers can like work with that as well, and then like try to come up with better optimization so that you can come up with, you can have like faster machine learning networks. So again, of course, like it's all in the pursuit of greater efficiency. So that's the idea.
And is it all greater efficiency, like low-level implementation, or is the idea that automatic differentiation is going to be kind of a different abstraction that lets us think about networks differently and do new things with networks?
I think the hope is that it makes it frees programmers from having to worry about like try to optimize computational graphs and all that kind of thing, and basically outsources that that workload to the compiler.
Okay.
And then you are able to use a more expressive language to basically like build more complicated neural networks, and so hopefully like frees the programmer to like experiment instead of having to deal with like more low level things like having to deal with the tape and all that kind of thing. Because the thing is that it's just like you can always optimize later, and like if you really want to optimize to the max, you can always I guess look at TensorFlow as well. So just a quick roundup of things that we've seen so far. That's the Scala one. They have a Lenten package over there. They use operator overloading, and they're really obsessed with trying to make their program transformation local. There is Haskell, which that was the Conal Elliott, and Conal Elliott is the guy who invented functional reactive programming paradigm, that co-invented, I think, and that's basically what Facebook's React is built on. And this is a bit more abstract, so I'll just keep on. So there's Julia as well. Michael Innes has written a paper there, Don't Unroll Adjoint. And the package Zygote, it's going to be part of this Flux framework that they're using. And it's working with the SSA-Form, which is related to ANF form. So Julia is also sneaking in some functional programming features in as well. In Python, there's this new package. It's still in experimental stages, alpha beta stages, but it's a blend of functional programming and computational graphs. Then they think that TensorFlow is doing something right with the computational graph, but they want to take it to a more functional stage. And the last one, Swift for TensorFlow. And they have a pretty big claim there, which is that they want Swift to be like the first general purpose differentiable programming language. So they've got a huge tutorial there. That's probably, but the idea is that you want programming languages that are general purpose, and they can also support automatic differentiation as first class operations in the programming language as well. So that's kind of the goal. And really, of course, the thing is that this is something that seems to be something that the compiler is really good at doing it. So the idea is, why do we let the compiler do it? And that and it's building on stuff that people have been working on for the past 50 years or so. The first paper that's been written about it was in 1964, and so now the paper is 55 years old already. There are still some outstanding problems, but I think more or less it's automatic differentiation. It is erasing heavy use, and the point here is to basically do it in a way that basically allows the programmer to outsource it to something that's closer to metal, and hopefully like that makes it faster and frees the people who are doing machine learning to not have to worry about that. Yep. Okay. Any more questions?
So do you know if PyTorch and TensorFlow is going into this direction of implementing the automatic differentiation in the framework so that we as a user don't need to do it?
Well, I mean, like, I think there's still going to be PyTorch and TensorFlow. I don't think I don't think those teams want to give that up. I don't think the users out there are going to give that up. But in terms of Python, I think I've just pointed out just now that there's this package called Maya, and it's still in the experimental stages. But I think there's definitely a push to try to like build that up, and yeah, so we might be seeing Maya in action further down the road. And like there's definitely, well, at least one person on the Swift team, I'm not sure if they're still there, who's really interested in making Swift like the first ever general purpose differentiable programming language. I mean, the whole idea is to try to make things easier for programmers, as in you don't have to worry about computational graphs unless you really want to, and that you can just easily like farm it out to the compiler and let the compiler do the job for you, and you just worry about the higher level of things like neural network programming patterns, and like maybe like you can build a new pattern or something like that, you know. And it's, I think, another effort to try to make experimentation more easier and more available to people who are just starting up.
So of all the resources that you have shared, for those of us that don't have a deep background in either functional programming or automatic differentiation, what's kind of the one place that you'd suggest we start?
The
Swift thing looks actually really interesting because it's both practical and implementable, and it seems to talk about some of the background as well.
I probably should have just.
And Jeremy Howard says that we all need to learn Swift next too, so that's we can get all the birds with one stone.
Okay. Look. I think this Swift manifesto over here is definitely a good place to start. I think because that definitely goes through like gives you a tutorial for automatic differentiation. Mm-hmm. For those of you out there who don't have the background, I think for the while, I think like PyTorch seems to be a little bit more friendly, I guess, unless you want to like optimize things a lot. And I guess like there's also Swift for TensorFlow as well at this particular moment. I don't know exactly when Richard Way's dream of a general purpose differentiable programming language will be realized. And I mean, so. Well, the point of doing all these, the point of all these developments is hopefully so that you don't have to learn all this. You don't have to learn all this to do machine learning. The whole point of like trying to like, you know, like I mean, like the point of this is to like try to like not have to like optimize computational graphs, not have to worry about a tape, not have to like worry about that. So if anyone out there is watching this from the future, I say 2020 or like us old timers are just like worry about like are we going how are we going to learn all these things? And the thing is, that's just like, what are you talking about? Like, we just plug and play, and we just, like, you know, like, we're just building neural networks for a high school project or something like that. Like, what are you talking about? Yeah, and like, we hope, I mean, like, the hope is to get to that stage when you're in the 2020s and you have no idea what we're talking about right here.
Hmm.
That's kind of the goal. We'll see how it goes.
Rongmin, I have a question for you.
Go on.
Can you hear me?
Yep, I can hear you.
Let's make this the last one, as we're just over time here.
Yeah. You choose in your earlier slide, you referred to automatic differentiation for the program block. You mentioned the term program block in your earlier slide, you know. Now, can I say that the program block is you know, equivalent to, let's say, an input layer, you know, the weights and the biases going into an input
you can
layer,
think of it.
and the activation function, the combination of the two. Is that a program block?
Including activation. Yeah, I guess so. Yeah. Basically, your intuition is correct, which is that you should think of you should think of a functional block. All right, what LeCun mentioned on his Facebook status.
Yeah.
A functional block is pretty much like a layer of a neural network.
Okay,
Yep.
okay, fine. Thanks a lot. It's a very hot topic, and thanks for your presentation.
Thank you for.
Thanks for the presentation. Good job. We learned something.
I think there's. Chris was trying to ask a question, but we couldn't hear him.
Can you hear me?
We can now.
Yeah.
Oh, you can. That's great.
Yeah.
Can I just ask my question, please, real fast?
Sure, sure.
Yeah.
Okay, awesome. I don't know anything about functional programming, but so this reminded me, and right at the end, it started making more sense that usually in C and C++, when you start to, say, for instance, you want to allocate memory, you usually have to use a pointer, and that pointer gets put on the heap, and the heap is very slow. And so you try to eliminate all of the possibility of your variables getting allocated on the heap, and so you try to stay on the stack as much as possible. And so the reason why you want to stay on the stack is it's much faster, and it's also managed by well, at runtime, it's managed for you, but the compiler will optimize a lot of things for you. So I wonder if these intermediate variables. Now I don't know anything about functional programming languages, but it sounds to me like there is a need for these intermediate variables to be optimized at compile time to do the differentiation very, very quickly. And so I wonder if that's kind of like they're kind of trying to buy maybe from the designs of like the C or the C++ architecture, where at compile time, when you go to compile your code, the compiler will see, okay, this variable should belong on the stack. This is a pointer. This should go on the heap, and then it'll kind of optimize that for you. And so I wonder if that's what this is kind of talking about, where these languages need to kind of develop that capability. Do you think that's...
Yeah, that's exactly right. Yeah, so like when I was talking about the tape, like, so people have been putting the tape on the heap. So what we want to do is what people have been trying to do right now is to put it on a stack, put the tape on a stack instead of on a heap. Let the compiler do it for you. Don't do it yourself.
Okay.
Yeah. So don't roll your own adjoint, as it were, to use Michael In's phrasing. So like don't create your own auxiliary data structure. Let the compiler do it for you, because the compiler itself is already monitoring, tracking such data using its own data structure. That's the stack that you're talking about, right? Whereas like what people have been doing in the past before 2008, they have been putting the tape on the heap, and like I don't know how TensorFlow is being implemented, but like I what I'm aware of is that like programmers have to like optimize the graph and all that kind of thing. That seems to be doing things on the heap as well. Maybe there's a reason for doing that, but it would be nice to do it on the stack instead.
Very interesting. Okay.
Yeah.
Thank you.
That's the idea. Yeah, and I think I've got it really well, actually. Like, I forgot about the stack and the heap analogy. Thanks for bringing it up.
Yeah, thank you. Thank you. All right, well, Rongmin, thank you so much. That was a great presentation.
Thanks for having me, Sam.
I'm going to be digging into this the Swift manifesto a little bit to try to understand this a little bit better. But that last question was really helpful, and I guess what my takeaway was that to try to represent more of what we're doing in a functional way, which kind of lets the compiler manage it as opposed to building it ourselves and needing to optimize all that kind of stuff. And that's kind of the takeaway.
Exactly. It's to make everything faster and hopefully simpler.
Yeah. Okay. Awesome. Well, thank you so much.
Thanks for having me.
All right. Bye-bye, everyone.